So in this tutorial we're going to cover how to set up a SolidCAM part. That'll be a new SolidCAM part, and a little bit about how SolidCAM stores your files, and we're going to look at a few simple milling operations once we're inside the SolidCAM interface. So there will be following tutorials after this one where we'll go into more detail, and we'll get further along with the machining operations to create this part that we're looking at here. So this part is available on the shoe site. You can see the part name up at the top of the screen here. It's TestCAM Model1 .SolidPart or SLD-PRT. So you can download that from the shoe site and then open that up in SolidWorks. So once you've got that open, you're going to need to enter the SolidCAM menu, and the way that you do that, it's inside the Tools menu up here, and you can see it just there. It pops up when I go down to the SolidCAM option. If you're not seeing the SolidCAM option, it may be that you've got the SolidCAM plugin turned off. So if you want to check that, you go down to Add-ins here, and then just find the SolidCAM plugin listed here, and ensure that this tick box on the left is ticked. So when you've done that, you should see the SolidCAM option in the menu. And before we get to producing a new part, we're going to just have a little look at one of the settings inside SolidCAM. So here's SolidCAM settings. We're going to have a look at the CAM part, and what we're looking for is the default setting that SolidCAM's going to use for the type of files that it's going to create. So you want to set this top option to external, and what that means is the folder that you've loaded your SolidWorks file from is the location that SolidCAM is going to save its files to. And its files can either be a .prt file or a .prz file. And we're going to set the system to the PRZ format. The main difference between these two formats is that the .prt file will save a SolidCAM file which will have the same name as your SolidWorks file, so this will be TestCAM Model1 .prt, but as well as that it will also save a subfolder in there with some other files in, and it's far neater if you switch the system to use the PRZ format, because the PRZ format is essentially a compressed version of this part file, this PRT file, and the folder that it would create otherwise. So it zips them all up inside this one file, and it makes for neater folders in your file system. So the way that we get it to use the PRZ file is obviously we have to have this option selected first, and then we're going to select this option down here, create new CAM parts in compressed mode, because that's what it's going to do. It's going to compress these files and the folder down into a single PRZ file. So the PRZ stands for a zipped version, which is just a way of archiving or compressing the files, zipping them. So yeah, let's select create new CAM parts in compressed mode. You can set the amount of compression here. If you've got any experience with using zip programs, you can compress them a lot, but it takes a long time to load and create those archives, or you can compress them not much at all. So I've got quite a lot of disk space, so I'm going to set this compression factor to 0, and then we're going to click on OK. You might want to play with that if you're running short of disk space, but you don't mind waiting for your files to load and unload, then you can set that higher and you'll get a smaller file. So once we've set those options in there, we're just going to click on OK, and now we can create our SolidCAM file. So if we get back into the SolidCAM menu, we're going to go new, and we're going to create a milling part file. This particular part, it doesn't require any turning on a lathe. It doesn't require a advanced sort of machining center called a mill turn system. We're just going to use the standard milling and then we get into the SolidCAM interface. So you can see essentially what it's done is it's just given us another copy of the part that we were looking at, but we're now in the SolidCAM interface. So this part is linked back to the solid part that we were just viewing. It gets all its geometry from the solid part. It's essentially a linked copy. So if you go back and change the solid works part and then close this down and reopen it, the system will detect that you've made a change in the SolidWorks model, and it will ask you if you want to run that change through into the SolidCAM copy. So we're just going to work down through this menu on the left hand side and set up our prerequisites for our machining operations. So the drop down menu at the top here is just asking us which CNC machine we'd like to use. So there's a lot of defaults in here. If we were programming for a specific machine, we would either find it in this list, or we would purchase a new machine setup and add it to the list before we created the part. But we're just going to select the default G-milling _3. So that 3 essentially means this is a 3-axis machine. So it has a table that will move in X and Z as we're looking at them here, and it has a turret that will move in Y. So the 3-axis G-milling is just the default one. Program number we're not going to play with at this point. We're going to leave that on the default. So the first thing underneath the CNC machine settings is the coordinate system. And the thing to understand about CNC machines is all the movements of all the parts within the machine all have to be referenced back to a point of geometry that is the origin point of all 3 axes. So essentially you have to pick either a piece of geometry on the part itself, or a piece of geometry on the piece of metal that you're going to cut the part from. So that would traditionally be bigger than the part, and you have to define that as the 0 point on the X, Y and Z axes. So all machining centers will require you to do this. So we're going to define a new coordinate system, and in this case we're going to relate the coordinate system to the geometry of the part itself. You can relate the coordinate system to the geometry of the block of material that you will be cutting the part from. That's an equally valid way to work, but we'll look at relating it to the part itself rather than the stock material that we're going to cut this part from. So we'll leave it set on the default option, which is select face, and we'll just pick this face on the side of our part. And you can see that what the system's doing there is it's creating this mesh work box that you can see pictured in pink, and that is a box which encloses the part. So there's no offset between the maximum extents of the part and the box itself. It's the smallest box, 6-sided box, that can enclose this part. So that essentially represents the limits of the part. And what it's also done is it's placed a coordinate system in one corner of that box. So by default it's picked this corner down here at the left. So what we're going to do first of all is we're going to move this coordinate system up to the top point here. So if we want to move the coordinate system at this point in the part setup, we click on Pick Origin and then select a different point. So if I select the point up here, you can see that the coordinate system jumps up to the top. And in this particular case, I've made a judgment call that I would like the Z axis pointing straight up out of the part, which tends to be how most machining centers are run. The X and the Y axes tend to be across the table of the machine. So there's a table that moves in X and Y. Those would be the horizontal axes, and then Z is reserved for the turret of the machine to move in. So Z will be pointing upwards. So let's try and rotate this axis round so that we've got Z pointing upwards and X and Y flat top of the part essentially. So we've got some flip options here. So let's start playing around with these to try and get Z pointing upwards. So you can see there, I clicked on the flip around X, and after a couple of clicks, I got the Z axis pointing in the direction that I want. Again, it depends whether you're the machinist or the machinist that you're working with or the company that you're doing machining for. There are lots of different ways of setting up your coordinate system, but one of the ways is that you point the axes or the legs of the axes away from the part itself. So you can see that the Z is currently pointing upwards away from the part, but the Y and the X are actually pointing towards the part. So let's see if we can point them away in the opposite direction. So for this I'm going to flip around Z. See if we can get them pointing away. So there you go. The X is still aligned to the same line here, but it's pointing away from the part now, and same with the Y. So what this means is that when you use SolidCAM to generate the G-code to send to your milling machine, any G-code positions that are negative numbers you can assume are cutting material away from the part. So if we look at the Z, all the positive numbers are from this point upwards, so there's actually no material up there that we're going to be required to cut. And then if we look at the X-axis again, because it's pointing away from the part, all the positive numbers on the X-axis aren't going to be cutting material, and then same with the Y as well. So some machinists will work in this way, other machinists will have the coordinate system down at the bottom of the part, so this doesn't hold true, this negative numbers, but we're going to set ours up just for this example in this way. So we're happy with that, we can click on OK. What we get to see next is this coordinate system data input box, and we can set things here like the tool start level. So the machine will maneuver the new tool into a Z position of 120, and this is positive 120, and then it will allow the G-code that we're going to generate in SolidCAM to take over the movement of the tool, but the mill itself will move it down to 120 millimeters above this coordinate system. So if we wanted to edit that, we could enter a value in there. That's okay. And then next down we've got clearance level. Some of these are technical terms that we don't need to go into at this point. Clearance level is essentially the level between operations, between milling operations. So the system tends to give you the option of taking your tool away from the part all the way up to the tool start level, or just maneuvering at clearance level, which tends to be lower. So if it was to take the tool up to here every time it moved to a different piece of geometry, you would lose time, because that's a further distance away from the top of the part. So you can play with these values. Again, we've got part upper level, which is set at 0 at the moment. That's because our coordinate system is sat on this top surface of the part. If we needed to change that, we could do. Part lower level, again, let's just select the bottom of the part just to check what that is. You can see that the Z level didn't change there at all. The X and Y is irrelevant, because when we go back to the entry box, you can see that it only registers the Z figure there. And again, we could go through all of these. We're not going to specifically talk about each one. One thing to note though is that you can manually enter values in here, or you can click on the button at the left and actually select pieces of geometry out of the part. So part upper level is what I'm picking currently, and if I wanted to link it to the top of this model, I just click there, and you can see my little collector circle there is stuck to the top of the model, so it's got the Z level as 0. And the nice thing about doing it this way is that these values will then be linked to the model. So if I make any changes to the model now, say I was to change the overall depth of it, that part lower level will automatically update. So rather than typing a static value, it tends to be better to link them to the model. So let's OK that. You can see that we've created that coordinate system there. It's listed in this coordinate systems manager, and we can see it in there. Later on we're going to add some more coordinate systems, but for the time being we're happy with that. So you can see we have a tick in the coordinate system now. So we've finished in that portion of the setup. We're going to move down to the next item, which is stock. So stock refers to the stock material that you're going to machine the part from. So this should be bigger than the part itself. It's very rare that you will size a piece of stock material down so that it's touching one of the finished faces of the part geometry. So what we're going to do is we're going to let the system use one of its automatic settings, and the setting that we're going to use is the box setting, which is very similar to the cage that you saw drawn around the actual part geometry. But what this one does is, if we just select the option there and then make sure that this both option here is selected, and then click anywhere on the part. Now what that does is it identifies the part as a piece of solid geometry, it enters it into this box here, and then it creates a cuboidal cage again, but rather than being on the surfaces of the part, this cage actually has an offset. So you can see I'm looking at it from each end, and you can see that the cage is actually offset from the part. And the offset values you can edit in these boxes lower down. So you have each axis as a direction, and you have a plus and minus offset. So as we've said, all the plus values are in the directions of these arrows, and all the minus values are in the opposite direction. So for our particular machining case here, I'm going to make a decision at this point that this slightly larger offset value in minus Z that you can see here, I'd like to increase that. So I'm going to put 10 in there. And in order to get the box to update in the display, you've got to click out of the box that you're editing. So I'm going to click in this one here, and you can see that the display updated there, and it's now a 10mm offset. So the reason for that will become clear later when we start to do some of the other operations. But one other option that we're going to switch on is we're going to click on this Add Box to CAD Model. Because if we don't click on that and just click on OK, the cage disappears. We can no longer see it, and it is quite useful when you're defining your machining operations if you can see some sort of representation of the stock material. So let's just drop back into there. We're not going to change any settings, we're just going to click on the Add Box to CAD Model, and then we can quit out of there. And you can see that there's now a permanent wireframe model or wireframe sketch representing the stock size round our model. So let's move down to the next option, which is Target. So if we've just selected the model to create our cage of stock material, our representation of stock material, this option is asking us to pick some solid material, so we'll pick the model again to represent what we're headed towards in all these machining operations. So this is our target model. This is what we hope to achieve once all our machining is complete. This is what we want to get out of the milling machine. So the system needs to know that for certain operations to work. There's certain more advanced operation types that will just look at the model geometry and move the tool accordingly with very little user input. So it needs to know what the target model looks like. So we've selected that. Part settings, we'll have a look at some of the settings in here, but we'll largely leave them on the default setting. This first one's to do with synchronization. Again, we talked about at the start that this SolidCAM file has a link back to the SolidWorks file that you created it from. And as I've already said, if you close this file down and go back into SolidWorks and edit the original SolidWorks file, and then save that. When you next load up this file in SolidCAM, you will often get a prompt informing you that you've changed something on the SolidWorks side, and it will ask you whether you want to carry those changes through. So there's a dynamic link, a one directional link from the SolidWorks file into the SolidCAM file, and you can manage those prompts from here. So we've got this check synchronization always, which is a good option to always have on. So every time it loads in a SolidCAM file, it will check the original SolidWorks file for changes, and then you can define its behavior once it's checked. So ask before synchronization is often useful, so that you as the user are aware of what's happening. Synchronize automatically, it will do that after it's asked you whether you do want to synchronize. It will automatically update everything. And then this last one, calculate operations after the synchronization. As we create operations to mill and cut material away in SolidCAM, any changes to the shape or geometry that you use to drive them doesn't automatically change the paths that the tools take. You have to actually recalculate each operation to update the tool paths. But we'll leave that option blank so that we as the user have the option of when we update the operations and the tool paths. There's an interesting one here that hopefully you won't have to use, the synchronization of a design model with original model. This tends to relate to if you move your SolidCAM part out of the directory that you originally had it in when you created the SolidCAM. SolidCAM will inform you of this. It will give you an error message saying something to the effect of, the SolidWorks file is no longer able to be found. Would you like to find the original model for me? So that's that option essentially. The bottom one we're just going to leave on the default again. Let's quickly run through some of these other options. This was one of the options that we were talking about before, which is between milling operations, move the tool through either the part clearance level or the operation start level. So again, this is to do with when one operation is complete and you're about to perform a second one, how far out of the part do you want the tool to raise to move to the next operation? Again, we'll not play with this at this point. Updated stock calculation, we're going to leave all these options as default. Machining process, we'll leave that as default. Default in there. We'll quickly run through these. I think we'll leave all the rest as the default settings. So the eye machining options at the bottom here we're not going to touch at this point either. We're just going to OK this because we can get into the SolidCAM interface now. So I think what we'll do is we'll just create a couple of simple operations just to get us started with machining this part. So probably a wise place to start is to machine away the excess material above the top surface of the part. So essentially, if we look at the part side on here, we have some stock material above the finished level of the part here. So what it would be wise to do is to send a reasonably large cutter in there and send it in some pattern, either backwards and forwards or maybe a spiral shape inwards, to machine away all this excess material on the top down to the level of this face here. So let's try and create an operation that does that. So if you right click on, I'll just OK that. If you right click on operations and go down to add milling operation, we're going to use the face milling option for this. So face is the operation type. So it brings us into this little interface here, which is face milling operation, but a lot of the options in here will be common to all the operation types that we perform. And the first option that we're going to define here is the geometry. So what shapes, either from the part geometry itself or maybe the stock box shape, do we want to use to drive the path of this tool? So the way that you define some new geometries, you click on this option here, which is the new geometry option, and then it brings you into the geometry selection box here. So I think what we'll do, as soon as we're in the face mill operation, we'll select face as type. So the type of selection that we're going to make is a particular face, and we'll select this top face as the face that we want. So I just clicked on define there, selected the top face. You can see that it's entered into the faces box here. You can also see that it's highlighted in pink, so we've definitely got it selected. I can OK that selection. What it's then done from that input of the face is it's drawn a rectangular boundary box around the outside of that face. So that is essentially saying it's going to try and machine away the material within that boundary. So let's say that we're not happy with that, because if we view that from above, you can see that the stock boundary is bigger than the boundary that it's created. So let's expand this boundary slightly so that we can be sure that we'll machine away these pieces of stock outside as well. So we can do that in offset if we want. Let's put a 5mm offset in there. Apply to all. You can see what it's done there, and now we're outside of the stock material. So let's say that we're happy with that. We can OK that. We'll move down, so we finished in the geometry menu now. We can move down to the tool menu. By default, it's looked at the operation type that we've created, so this is a face mill, and it's tried to supply us with a likely tool that we would use for this operation. So in this case, you can see I'm rotating this round in the little window here, and what we're looking at is we're looking at a representation of this face mill tool that it's created for us. So it has a cutting diameter of 50mm, so this yellow portion down the bottom here, that will be a 50mm diameter. It has a cutting height, which is what this is, this 20 of 20mm, so that upright there, which is also coloured yellow, will also cut material. So you could send this tool into the part sideways, as long as it's not cutting deeper than 20mm, or depending on the type of tool that it is, sometimes you can enter from directly above. But the yellow portion there represents the bit that is toothed, that can cut away material. And then outside the holder 40, if we click on select here, we can get a more detailed view of what these figures mean. So you can see here, you can define all the different geometry that defines a face mill, and you can see a representation of a face mill here, and all these different values are indicated on here. But let's say we're happy with the default tool that it's given us there. What we might want to do next is maybe change the RPM that we spin the tool at, or the feed speed that we're going to maneuver the tool through the part at. So we could change those values in here, and we will talk about that later on. But again, let's assume that we're happy with all the default values in there, and we'll go to the next option down, levels. So this is going to define how deep we're going to cut the material away. So clearance level, we're going to leave it at the default clearance level for the part, which we set when we were setting the part up. Safety distance we're going to leave as the default. The upper level, so these are the milling levels that we're talking about here. The upper level in this case would be the top of the stock material, because we don't want the tool coming in at a very high speed and smashing itself into the top of the stock. So we need to tell the system where it needs to begin its milling operation, so where it needs to expect that there's some material. And now that we've put this stock box wireframe so it's visible in the part, we can use it to click on. So we can click on any one of these top points or edges, and that sets the value at 2. So that's correct because our coordinate system sat on this top face and the stop box is 2 mil above that, so we can check that that's correct. And then the face depth that we're going to machine down to in this operation, so if we select face depth, corresponds to this top face of the model, which again in absolute terms is 0 on the z-axis because this coordinate system is sat on top of that surface, so we can be happy that that's okay as well. What we can see when we come back here is a value of 2 seems to have put itself in the face depth, and all that means is its absolute value in x, y and z is still 0, but it's 2 mil away from the upper level. So that's all that means. It's just calculating the distance between where it's starting and where it's going to end, and the difference between 2 and 0 is obviously 2. So there's one final option here, which is the step down, which every time we enter one of these options you can see that the graphic at the left hand side here is changing and it's trying to tell us what these options are going to do. So the step down option is related to if the depth of material that we're trying to clear out of the way is too deep for the tool to handle in a single pass, then you can take that material away in multiple passes. So you can see our face mill here, you can see a representation of it dropping down into the part and then machining along in this direction, and then dropping down again and then machining along, and then dropping down again and then machining along. So it's not taking this full depth as one cut, it's taking it in step downs. So we've got to clear 2 mil of material, which for a face tool such as this is probably perfectly achievable, but let's reduce it to 1 just to make it do 2 passes to clear the material. So we're happy with that, with those settings now as well. Let's move down to the next tab, technology. At this point we're going to have a look at what the tool is going to do currently. Before we start playing with the technology tab or the technology menu, what we're going to do is we're going to click on this option, and again these options are common to all operations along the bottom here, and the one that you're going to end up clicking on a lot is this save and calculate. So I'm going to click on that, and it takes it a second to calculate, and then what is now available to me is if I tick the checkbox at the side of my face mill operation here, I get a preview of how the tool is going to move using these settings that I've defined up to this point and using the default settings in technology. So you can see, just for reference, the technology that it's defaulted to is a spiral, which tallies with the tool path that we're looking at in the graphics window here. So you can see this is the start point of the tool, and then the red portion of this line is where the tool is moving at a rapid rate. So it moves all the way down to here. You can see that it then turns to green, and what that means is the tool slows down at this point and starts to move vertically quite slowly. And that's just to be cautious when entering new parts, but we can change that. That's to do with the clearance levels. So it's to do with upper levels and clearance levels and start levels. This is when the tool starts moving more slowly. And then it moves down to this top blue line here, and it follows the top blue line along its length. So this is the center axis of the tool, remember. So if the tool has a big diameter, then it will be cutting a lot more material outside of this line. So obviously the tool comes round here, it goes around and around, around and around, it's spiraling inwards, and then when it gets to the center point, it moves at a rapid rate again. That's why this is red. Back out up to the clearance level, and then back along to the start point, and then it goes down and it cuts this bottom spiral. So the fact that there's 2 spirals is linked to this level setting where we set the step down to 1. So let's play around with this now, and let's set the step down to 2, and then do a save and calculate, and you can see that that second spiral has now disappeared because it's happy to cut that material away in a single pass. So let's put it back to step down of 1 and save and calculate again. So this will be the mode of operation in a lot of the milling operations that you're going to create. You'll sketch out the milling operation, you'll put the basic values in there, and then when you've put enough information in, you'll probably hit save and calculate, and you'll start analysing what has been created by SolidCAM and changing the values, and then analysing it again. So changing the values. So let's play around with the technology portion of this. In fact, let's see a simulation of what this is going to look like. So we're going to click this simulate tab, or this simulate button here. This brings up the simulation interface, and I think there's lots of different methods of simulating this. A common one that you may use a lot is the solid verify. So we'll use that one in this case. You can see we're looking at our stop block here, and then what we're going to do is we're going to ensure that the simulation speed is way down at the bottom so we can see what the tool is doing, and then we're going to hit play. So you can see the tool coming in, you can see it tracing its spiral path as it comes in. So it's cutting a certain amount of material if we watch it from the top. So if we pause it there, you can see that there's a depth of material or a width of material that it's cutting there, and we're going to play around with that later on. So that's essentially how much it's stepping into the part to cut. So let's watch it some more. So that's the first level of cuts, and then we should see it come vertically out of the part and come back to the start position. So let's watch for that. So there it came, it was quite quick, it lifted up and out of the part, and now it's come back for the second pass. So let's just speed the simulation up so it gets to the end. So that's the end of the simulation. The material's been cut. Now if you select this option here, which is, if I hover over this, hopefully we can get the tooltip to show. There you go. Show or hide rest material. Rest material, you can essentially think of it as it's the rest of the material. It's all the material that has not been cut yet. So let's select that. But more than that, it's all the material that is yet to be cut. So everything in red there needs to be removed from the part. But we can see the part itself in this sort of grey blue is starting to show through, and that's because we've used that face mill to cut down to the finished surface. So this will be the finished surface of the part. This is not going to require any more machining, this surface, but everything in red is yet to be cut, so it's rest material. So that's quite a useful visual tool to be able to just click on to see how close to the finished part your last operation has taken you. So let's quit out of there. Right, let's start playing around with these cutting passes. And what you're going to tend to be doing is you're going to be simulating operations, and then you're going to be looking at this value here. So this is the time taken for that operation, 3 minutes and 20. And one of the things that you're going to be aiming to do is to achieve the same amount of material removal but in a shorter time, whilst not overloading your tools. So later on we're going to get into looking at feeds and speeds for tools, and if you start pushing tools too aggressively, so either spinning them too fast or pushing them through the material too quick or cutting too much material in each pass with either a really big step down or a really aggressive step over, then the tool will have a reduced lifespan. You may damage the spindle of the milling machine, and the surface finish that you're going to get on your finished machine surfaces is going to be very poor. So you must be aware that you can't get time back simply by increasing feed values and spin rates. You've got to do it to a certain extent by doing that within sensible limits, but by using the technology and the methods that you're removing the material. So let's look at some of the other methods. We've got spiral. Let's look, and again we're getting a hopefully a representation. Let's click on hatch. So you can see there, hatch pattern travels along the part and then it moves across and then comes back and then moves across. So let's do a save and calculate on that. You can see what's going on there. We can simulate that as well. Let's reduce the speed down of the simulation again. So it's hatching backwards and forwards. And we had 320. We've saved a slight amount of time there. We've saved 3 seconds, so almost identical time. But again, there's lots of different options to play with here. Spiral we had, contour, let's try contour. Contour is very similar to spiral, and the reason for that is, in fact, it's not. It's doing multiple passes. Let's do the solid verify. Let's reduce the speed. So it's taking multiple passes, but it's not joining them. It's coming up and out of the part in between, but it has achieved a lower overall time. So that might be one that's worth looking at. So at this point, let's save and calculate that. So it saves to the hard disk, and I think we'll leave the first tutorial there. So we'll pick this up in tutorial 2 and add some more operations.